Welcome to this session on storage appliance services and nvme-stas. I'm Claudio DeSanti from Dell. As I said, this is not my presentation. This presentation was supposed to be delivered by Martin Belanger, who is the programmer and designer who coded and programmed this software. But he could not travel here, and so I'm replacing him delivering this presentation. So this is our agenda. We are going through the motivations for nvme-stas, how it works, how you can get it, how you can use it, what is on the drawing board, what we plan to do, conclusion, why this is relevant. So, motivations. Main motivation for nvme-stas is to automate host configuration. In nvme.org, in the FMDS working group, we completed and ratified two technical proposals. One is TP8009, which is called Automated Discovery of NVMe-OF Discovery Controllers for IP Networks. And the other one is TP8010, which is NVMe-OF Centralized Discovery Controller. These two technical proposals define two protocols, one based on mDNS to perform automatic discoveries of discovery controllers over a local area network, over a local subnet, and the other one to define the concept to access the centralized discovery controller that is able to centralize the information of all the entities that are present in the fabric. Okay, so what nvme-stas does, it implements these two protocols on the host side. And implement one of the fundamental functions that TP8010 also defined is fabric zoning, the ability to restrict or to define connectivity configurations. Means host A and B can access subsystem C, host D and E can access subsystem 1, and so on. So this is what zoning in Fibre Channel traditionally does. And so TP8010 defines the same type of functionality over the centralized discovery controller. And once you have you define zoning, zoning is something that is subject to administration. So it's something that can change. And so you can have, now this host A, is able to access storage 2. At another point, the fabric administrator may decide, no, I don't want any more storage due to be allocated to host C and to be allocated somewhere else. So there can be connectivity configuration changes as a result of fabric zoning changes. And so another thing that nvme-stas does is able to react to these connectivity configuration changes as dictated by the fabric zoning configuration that is currently enforced by the centralized discovery controller. And so it makes sure that host can connect or disconnect to and from the subsystems when the connectivity configuration changes, and provide also a configurable connection audit mode to remove the connections that are not anymore allowed if you choose to do that. So, briefly, why do we need this type of automation? And here we get straight to your point. If you don't have 8009 or 8010, and you want to be able that an IP host connect to an NVM subsystem, how that would work? Well, first you need an administrator need to supply an IP address to the host, and that is a manual step, and this enables the host to connect to the DDC that is hosted on the NVM subsystem. You can have the storage administrator that provision namespace to the host NQN. At this point, the host can do what in Linux is called a connect all, to basically discover from this DDC all the controllers that are accessible or the namespaces that are accessible to the host and connect to those in order to establish IO connection to the system. So this is what is happening. The fundamental problem of this thing, something that also Kamal in his presentation yesterday was noticing, is that there This is something that has to be done for every host that you have on your fabric. And there is a manual configuration that needs to be done. So it's a manual process. And that is the fundamental problem that this has. Once you add TP 8009, 8010 into the picture, okay, now you have, first of all, you reduce the problem of connecting to discovery controller to connecting to one discovery controller. You have a centralized entity, so rather than connecting to n DDCs, now you can connect to just one. That is what TP 8010 allows you to do. And then with TP 8009, you are able to automatically discover this CDC if it is located on your local subnet. And so the step that you have, first, host and subsystem automatically discover the CDC thanks to the mDNS protocol defined by TP 8009 and register discovery info on the centralized discovery controller. Zoning can be performed on the CDC, so you have this central fabric policy configuration that is done on the CDC itself. Then the storage administrator can provision namespaces to the host NQN, and it's possible also to have what we call subsystem-driven zoning information sent directly to the CDC. And at this point, after zoning, an host will receive an asynchronous event notification that tells, okay, your connectivity configuration changes. Go to figure out what happened. The host issues a get discovery log page to the centralized discovery controller that provides the list of subsystems that are accessible to that specific host, and the host now can connect to each I/O controller. So what is happening here is that this is now an automated configuration. There is no manual configuration that is required of the host. nvme-stas is basically this open source software that implements this new protocol, 8009, 8000. So how it works? A few definitions, because these are used here. We have terms discovery controller, that can be DDC, direct discovery controller, co-hosted in an MVM subsystem, or CDC, centralized discovery controller. IOC is an I/O controller. Fabric zoning, as I said, defines the connectivity relationship allowed within host and subsystem entities, members of the same fabric. So the entities that share a common zone, so are zoned together, are allowed to discover each other and establish connection between them. Then a discovery log page is what is returned by a discovery controller in response to a get discovery log page command from a host. A discovery log page is composed of 0 or more discovery log page entries. Each discovery log page entry identifies a controller that the host can connect to, and discovery controller will already return discovery log page entries for discovery controllers and I/O controllers that are zoned together with the host. So everything is subject to the rules of fabric zoning. And finally, asynchronous event notification is the equivalent of an RSCN in Fabric channel on the IP network. It's a completion queue entry for an asynchronous event request that was previously transmitted by the host to a discovery controller. And the AEN is used for our purpose to notify a host that a change, example, a connectivity configuration change, has occurred. So, how does it work? This is the diagram that shows how a Linux host implements this functionality. This is what Martin basically did according to one of the fundamental Linux principles that are you have one daemon per each function and you don't mix function on different daemons of different processes. So Linux already has the Avahi daemon that performs 0 configuration and is able to handle mDNS requests and responses. So there is no need to reinvent the hot water, reinvent the wheel there, it's just used. That is the first piece. And that is what is used basically to get mDNS queries and responses and discover CDCs or DDCs along these different networks. You can see in this diagram there are independent networks. In each network, Here you can see you can have a CDC or a DDC or another CDC and multiple DDCs. Then, another important piece is UDFD, the user space device daemon. This is a conventional event service for devices that is able to relay kernel events to applications, and that is used whenever something is detected by the kernel, basically to pass these events to the staffd daemon. Staffd is the storage appliance finder daemon. Basically, this is the process, the daemon that is communicating with discovery controllers and getting the discovery log pages, discovery log page entries, and figuring out, okay, this is where I can connect. That's what it does. So, of course, it does locate discovery controller thanks to the Avahi daemon, or through a manual configuration file that you can have that specifies IP addresses of CDCs and DDCs. You have both of these possibilities. You can leverage the mDNS for your local network, or if your CDC is not local to your subnet, and so mDNS will not work, you can just configure the IP address of the CDC that you want to reach. This staffd, once gets the IP addresses of the discovery controllers, is able to connect to all the discovery controllers of pertinence. You can see per each network independent network interface, you can connect to a centralized discovery controller here, to a DDC here, or to another CDC here. Once it connects to discovery controllers, perform the explicit registration, what is called the dim command, issue the get discovery log page command to the discovery controller, and in this case, and so in this way, all the discovery log page entries related to this host are retrieved by staffd, and everything then is put in its own cache of discovery log pages that is kept up to date. Anytime an AEN is received by a discovery controller, staffd again is the daemon that will issue another get discovery log page to refresh the list of discovery log page entries coming from that specific discovery controller. So again, the purpose of staffd, Store Appliance Finder daemon, is really keep a list of discovery log page entries that are actual and current for this host, and are describing NVM subsystem or I/O controllers, basically, to which this host can connect or can be connected. And yes, please.
So in this process, as I look at your diagrams, I note that the left and the right storage networks, you have a central discovery controller.
Correct.
And your staffing reaches down to the central discovery controller. But in the central one, you don't have the central discovery controller, so it sees the device directly.
It connects still to each NVM subsystem hosts a local discovery controller that is called direct discovery controller, and so staffd doesn't distinguish in a sense between CDCs or DC. It handles both in the same way, also because the protocol is the same. You do a get discovery log page to a CDC, or you do a get discovery log page to a DDC, and you get the discovery log page entries that are related to do according to that discovery controller.
So the central discovery controller to the left and the right, they gave hosts to zoning tools.
Correct.
What prevents your staff from seeing the direct discovery controllers to the left and right network? Why do they see past? Why do they not see past the central discovery controller? Is there a phased approach or something?
Okay. That two answers to that question. First, easy answer. If you have a configuration file that tells you, please connect to this IP address, and you configure over there just the IP address of the two CDCs, it will connect just there. The manual configuration approach. Second, the auto configuration approach. In TP 8009, we described that when mDNS is something that runs on each of the DDCs and can run on the CDC. When a DDC detects on its own network there is a CDC, we specify that the CDC should stop replying to mDNS queries, and just the CDC does. And so when you perform the discovery on a network where there is a CDC, you connect to the CDC. Kind of invisible, because the fundamental logic over there, you reduce to one the problem of discovery. You have a set of DDCs, the CDCs is grabbing the information from all these DDCs, collapsing in a single database, and now you just have to connect to a single entity and you get all the information that you need. Filtration by zoning rule is all in the CDC, correct. Yes?
There can be more than one network.
It's theoretically possible to have more than one CDC in the same network. It's not a recommended configuration, because then you don't know in a sense where basically which one you need to handle or so on. Don't remember if we have something there. Curtis, do you remember if we put something there? No.
No, the recommendation is one, but there's probably going to be some more things in the future as people learn about these things. One of the things we wanted to allow for was communication, creating highly available templates for the controllers, which may require having two in network with some sort of reference, maybe some sort of a load balancer in the system. Looking at this further is but it's really recommended to be a only play one where interoperability is possible. So the list moves up, discovers the CDC, don't broadcast it.
Yeah, exactly. So the basic idea is, yes, if you want a workable configuration, you have one CDC per local subnet. That's what you are looking at. Okay, any other question on this? Good. So once we are to this point and get an AEN, everything is refreshed. Every time the discovery log pages are changed, staffd use the dbas, which is a normal communication channel among processes on Linux, to basically send this notification to stackd instead. And stackd is the storage appliance connector daemon. This is the daemon that gets the list of discovery log page entries, each describing a subsystem you can connect to, and establishes the connection to these subsystems. So gets the list of the subsystem that you can connect to and set up these I/O connections to all the storage appliances. And then it monitors and reacts to these discovery log page changes messages that can get from the stackd. So whenever there is, as an example, a fabric zoning configuration changes that cause a connectivity configuration change, this is discovered by staffd, because there is an AEN that arrives on the staffd daemon. A get discovery log page sent by staffd to the discovery controller. A new set of discovery log page entries is retrieved, and at this point, the stackd gets the information of what is changed and can now act to the changes. So reacts to discovery log page entry changes, and can add or remove I/O connections are necessary. So if you, as an example, if the storage administrator add 2 new storage subsystems that now are accessible to this specific host, you will get an addition. You will be able in this way to automatically connect over there. So, and finally, we have these two programs, utility programs, staff CTL and stacked CTL, that are basically used to display information from the two daemons, staff D and stack D. That is basically how it works, what is the full configuration of the processes that enable to implement these protocols. The component of dependencies, there are pieces part of the Linux kernel, NVMe, TCP, Fabrics, and Core. It's based on the open source library libnvme, and that basically what is used by both staff D and stack C. As I say, implement 8010, 89, also 8013, which is the unique NQN for a discovery controller. These are the kernel versions, Linux kernel version that support these things. So, this is entirely written in Python, and it has dependencies on these Python modules, dbas, pudev, gobject, systemd. Don't ask me too much about them. I'm not the guy who did this coding, as I said. It is distributed under the Apache 2 license. Processes use, as I say, dbas to talk to each other, and this is conventional Linux inter-process communication. And it also defines an API over the dbas, which is used by the control program, and also allows third-party application to interact with the two daemons and can be used for automation and testing. How to get it? It is an open source project. It is hosted in the Linux NVMe GitHub project. Same location as libnvme and NVMe CLI. Debian, Red Hat, SUSE already package NVMe CLI from this location. Dell is the primary maintainer for the nvme-stas repo. And again, it's open source and open to contributions. How you do install and run it? It's currently available with SLES 15 SP4, and using that command you can install. Is expected to be included in RHEL 9.1 as tech preview. For other distributions, you build and install from source. It uses the Meson build system like libnvme. Of course, whenever you build it by yourself, no implied guarantee that it will work. You need to meet all the dependencies and look at the documentation in order to see what is there. Of course, it's a Linux set of daemons. They can be run in a container, and in the repo you can find an example on how to run them in a Docker. How to use it? Here is the documentation. There are man pages. Documentation is available on the network, and on the GitHub you find all the information you can find for every piece of this software distribution. Direct configuration. As said before, it works right out of the box without any manual intervention. This is, you see, an example configuration for staff D, because zeroconf is enabled, which means it's using mDNS discovery by default. But the configuration file allows to tweak and configure the operation of staff D in staffd.conf or staffd.conf. The configuration file is self-documented, everything is written inside, and there are also man pages that are available. Let's look at some specific configuration parameters. Global parameters, you find the Cato, 30 seconds, trace on to journal, everything that happens is by default is false. Supports the possibility to have a header digest and data digest in the PDUs, which is set to false by default. And in terms of IP family, by default supports both IPv4 and IPv6, but you can select which one you want to use. Zero-conf in terms of service discovery is enabled, which means everything is automated. And you can, as I say, specify some controller manually, both in positive way, controller, here you have all the addressing information of a specific controller you want to connect to, or negative way, say exclude, please do not connect to the specific controller even if you discover it. So this is a way in which if you are in a configuration and on a network you have a few controllers, you want to be sure you connect only to one, well, you can use this configuration parameter to try to work around that issue. In the stack deconf, stack D, remember, is the one that set up and monitors the I/O connections. You have a same global configuration of stack D, except Kato is default to 120 seconds. And here there is this interesting I/O controller disconnect policy. Connectivity to NVM subsystem using NVMe TCP so far has been done using NVMe CLI. And the way in which NVMe CLI works, once you connect to a subsystem, that connection continues to stay on, is not turned down unless the administrator decides with another NVMe CLI command that connection has to be removed, or unless, of course, the NVM subsystem becomes offline. Here, instead, we say that everything is automated and you are supposed to respond to connectivity connectivity configuration changes as a result of fabric zoning configuration changes. And so we have this section instead they called I/O controller disconnect policy. Every time you add a new subsystem, what to do is fairly straightforward, just connect and go there. But what if how should the host behave if the zoning configuration says, okay, you are connected to this subsystem and now you are not anymore supposed to be connected to this subsystem? How do you do this disconnect policy? By default, the way in which it does, stackd monitors only the connections that are done by SDCs, but are done by these two daemons, and not what you configure manually. So by default, only those are monitored, and if fabric zoning decides now you should not be anymore connected to this specific subsystem, it turns down that connection in the moment in which the discovery log page entry is not present once you issue the get discovery log page command related to that subsystem. So that is the default behavior. But given that this is a new behavior, is now configurable. So disconnect scope, stackd can monitor only the status connection of all the connections, or can be no disconnect. Which means once you connect to a subsystem, no matter what happens to the discovery log pages, that connection is not removed automatically by the host. And over which transport this disconnect is acted, by default is on TCP, but it can support basically all transports can be monitored in the same way. So that's basically the fundamental point here that shows how this stackd daemon is able to react to fabric configuration to fabric zoning configuration changes. The future of nvme-stas, well, stuff that is currently on the drawing board. The fundamental thing here, again, many of these things are really things to look at, not clear yet what will go over there, but certainly an eye on security, support the AV discovery log page, a new discovery log page that has been defined for something that will be discussed in the next presentation, or work with authentication on TLS connection that is on the drawing board for the next revisions. Very important things is also completing the support for 8010, TP8010, specifically using the port local entry only bit to get only port local entries when retrieving log pages, or the conditional connect based on the no CDC connectivity bit. We define in 8010 in each discovery log page entry this bit that basically says, oh, look, this subsystem is present in the name server database of the CDC, but now the CDC does not have any more reachability to that subsystem. And this is an information to the host that if IOs are going fine to that subsystem, okay, that is a connectivity issue between the CDC and the subsystem, has nothing to do with the host. But instead, if the host also doesn't see anymore the subsystem, don't try to reconnect, because it means that subsystem most likely really went offline. So, additional things on IO reconnect policies, multi-driver support, and other things. This is all stuff which is in the drawing board for the future. Nothing committed for the moment. Conclusion. When to use this? Again, as I said, nvme-stas is an open source implementation of TP8009 and TP8010 for Linux. And so it enables automatic discovery and connection to discovery controllers, allows to adapt to connectivity configuration changes as a result of changes in fabric zoning configuration. And it can work, it does not replace, it can replace NVMe CLI, but the two things are independent. So it can work in parallel with NVMe CLI, which allows you to do, let's say, some sort of manual configuration of your storage connectivity. But of course, every time you have two things that do the same thing, be careful about managing conflicts between the two things. And so one of the things on the drawing board is also work on a conflict detection or resolution tool in the moment in which what is being done on the NVMe CLI does not match what instead is automatically discovered by nvme-stas. And this was it. Any questions? Comments? Please.
So the fabric zoning changes that gets advertised or that gets broadcast to the host, does it also get broadcast to the storage? Because the host don't behave well when zoning is connected to the fabric changes, zoning changes. Is there a way where target can host disconnect?
The fabric zoning changes cause a change in the discovery log page related to a certain subsystem. Whenever you have a change in a discovery log page, whoever registered to get a notification for that change will get an AEN that says, hey, that discovery log page has changed. At this point, the host can connect to the CDC and get that information. Also, a subsystem can connect to the CDC and get the same information. There is nothing that prevents that. Yes?
But the NVM subsystem doesn't implement any form of filtering based on zoning configuration. It doesn't know zoning configuration, right? The direct discovery controller.
The direct discovery controller does not, but repeat the question. The question is, but this subsystem does not implement the zoning, the direct discovery controller. That is correct, but each subsystem in any sense does what is called namespace mapping or namespace allocation to NQNs, from which is kind of an implicit zoning configuration. Because in the moment you say, okay, over this subsystem, I've defined these X namespaces, and I want 1 to 3 associated to host A, 4 to 7 to host B, and so on. This, in a sense, is a filtering information that the subsystem has, although it's not what you call zoning information, because it's not based on network connectivity, but it's based on namespace access information.
But you could apply your connectivity, your zone to whether namespace.
That is the concept of subsystem-driven zoning, in which, okay, you do this namespace filtering configuration. From that, you derive at zoning information, and at that point, the subsystem can send this information to the CDC for so that filtering can be acted also on the CDC.
Yeah, that works well if you're
Yes.
Pole communication, pole direction is fine. So if you subsystems are going, the subsystem defines the rules and sends them down into the CDC, or you can do zoning at the CDC, and the subsystem can discover the zoning information, and if the company shows clinical energy, the subsystem could enforce the zoning rules of the CDC and pull them out.
Which seems like a safe way to do it.
Which one do they?
Where the central discovery controller sends the zoning rules down to the subsystem and the NVMe subsystem. I mean, if the CDC goes away, or there's a bogus CDC that comes along, or somebody hacks the information on the web system, or a million different possible thing, it feels like we want the default behavior to be that the zoning configuration that the last installed continues to operate until this thing figures itself out and stands itself back up and gets back on its feet, right?
It depends on where your admin gets it. If you have a central, if you have an admin interface, you have to always be focused there. But if your admin interface is focused on the NVMe subsystem,
Then you have a way to pass that information from each subsystem to the CDC.
so it goes both ways.
Yes.
Regardless of where it's configured, I feel your subsystem will be aware of the and enforce all the rules.
Okay.
That if the zoning rules start out with subsystem,
Yes?
I thought you have SDCs in that your future.
Yes.
So my question is, for the current state, does that work if I have a CDK targeting template different system? Is the current way to work as it is?
Right now, just use libnvme in the Linux kernel. So there is no optimization done to use SPDK. That is the current.
But the general discovery thing.
Yeah, well, that is a protocol, so it will work.
Second question, I also thought you have AENs, United, DSS. So for that integration,
Let me go back here. Okay.
does that mean you're going to pick those and then right now my understanding is those individual storage with all single hosts, right?
Correct.
Yeah. That in the future you have line to kind of putting those hosts as storage, different storage into different kind of more distributed into kind of using the Kubernetes as a control plane.
You know, these are all possibilities. Again, this is a piece of software that implements these two fundamental protocols. How that matches with that host configuration is really a matter of how the host is done. If you have a monolithic Linux server, okay, you just put it and put it on. If your application or your host configuration is all based on Kubernetes and containers and so on, you might want to have this thing containerized and access and limit the operation to specific containers. So that is the kind of thing that we are investigating. Anything else? Thank you.